Hi, welcome to the second part of Lecture 9 of EEE 107. We're still talking about analog pulse modulation, but we will now be talking about the variants. The variants, not the variants, variants of analog pulse modulation techniques and multiplexing systems. So in the previous lecture, we talked about the ideal sampling and the natural sampling schemes. Where ideal sampling, we have a series of impulse, impulse functions, an impulse train that we use for sampling, but in reality, we can't really implement that. So we use something close to that, which is rectangular pulse. We use it for natural sampling, and in effect, both of them create aliases of the signal in different parts of the frequency spectrum. Okay, and we need to sample the signal at more than twice the bandwidth of the signal, more than twice the highest frequency content of the signal, and that's your Nyquist sampling theorem right here. So a variant of your pulse modulation technique is the pulse amplitude modulation. Instead of multiplying your rectangular pulses to your natural to your message signal, we're creating curves in the curves in the creating some form of envelope in our pulse modulated signal. A flat top sampling kind of works as an ideal sampling case in which your signal is sampled here, okay, and then it will have the same value until the pulse becomes 0. So what the sampled value here, your signal maintains that value over the whole pulse width. Okay, so the pulse value is maintained over the whole pulse duration or the pulse width. So your PAM signal can be expressed in this form, where it's similar to, sorry, oops, oh, sorry, let me just, okay. So it's kind of similar to your sampled case, at which you have your ideal sampled case. There you go. Yeah, there's some form of similarity between them, right? But instead of having a delta function as your pulse, you're using a rectangular pulse, h of t, as your pulse. Okay? And the definition of t is right here. So for ideal sample, it's actually here, so I did not see it. So anyway, okay, so we can relate then the ideal sampling and the flat top sampling by convolving the ideal sampled signal with the transfer function. So we can get your pulse amplitude modulation, your PAM signal, using your ideal sampling convolved with the shape of the pulse. So this pulse can take on any form. It can be half cosine pulse. It can be some weird triangular shape, and so on and so forth. Okay, and these pulse shaping techniques are also studied in digital communication systems, where some pulse designs are actually more optimal than the others. So in the time domain illustration for that is your m of t will be sampled ideally. So it's multiplied to a pulse train, and then it will be convolved. And since we're convolving, in the frequency domain, you just multiply, okay, your message signal to your pulse, to your the Fourier transform of the selected pulse. What happens is that since you multiply it, your signal will have some form of distortion. It won't be in the same shape as your original frequency spectrum. Okay? So it follows the shape of h of f, and this is called the aperture effect. So if your ideally sampled signal has this spectrum, if you pass it through some pulse h of t, the output will be distorted as you see here. So the pulse shapes your sampled signal, and to reduce the aperture effect, you need to have narrower pulses. Okay? Because if you use wider pulses, your sync lobe will be smaller, so this distortion could be uh, worse. Okay? So the rule of thumb here is the duty cycle of your pulse should be less than 0.1, so that you have less than 0.5% distortion of the signal. Otherwise, you have to use an equalizer so that your signal will be restored to its original shape. So that's what's happening here. We use an equalizer so that we can recover the signal. Okay. So if we have a negligible amplitude distortion, it would be more practical to omit the equalizer though. Alright, so just to compare the natural sampling and the flat top sampling case, your natural sampling provides constant scaling on each replica. So as you can see, the message signal is not distorted. But for flat top sampling, your pulse shapes the output of the message signal. Okay? So this is where pulse design becomes important. So if you design the pulse properly, you will be able to transmit a flat top sampling signal that is not distorted when we try to recover it using your low pass filter. Okay? So another form of analog pulse modulation is the pulse time modulation, which can be broken down into two: your pulse width modulation and your pulse position modulation. So the first one is you vary the width of the pulse by its name. The other one, you vary the position of the pulse by its name. So if you have the same signal here, the pulse width modulation is something like this, okay? Where you increase the duration of the pulse depending on your sampled signal, the level of the sampled signal at that point. And it's related to the pulse position modulation, as you can see here. When the pulse width modulation ends, right? The pulse width modulation ends, that's when the pulse appears, as you see here, and so on and so forth. Okay? So mathematically, your PWM signal can be described as this, where your pulse is 1 depending on the message signal multiplied by some sensitivity or scaling factor. So the scaling factor relates the amplitude of the message signal to the pulse duration. Can we analyze its frequency domain though? Yes, we can, but it's quite difficult. And it's used more often in power electronics for digital control. So PWM is used for digital control, for controlling the DC component of your motors, and so on and so forth. Okay. To produce a PWM signal, you have to use a reference sawtooth waveform and compare it with your signal. Use a comparator for that. By using a comparator, whenever your sawtooth signal is less than your input signal, okay? So whenever it's less than your input signal, it will have a low value. And when your sawtooth signal is less than the input signal, your pulse value is high. Okay? And the frequency of the sawtooth signal would be the sampling frequency of your PWM signal. Okay? Now, for your pulse position modulation, you can mathematically describe it as follows. Instead of a piecewise function, it's just equal to this, where your time delay is dependent on the message signal. So the message signal defines when you will shift in time. And it's related to your pulse width modulation by, well, just connecting a pulse generator that will activate when your PWM output goes from high to low. So this pulse generator is triggered by transition from logic 1 to logic 0. Okay? And it will generate a pulse of some duration, okay, depending on the setup of your pulse generator. Okay? So a lot of this actually, forgot to mention, are used in digital control systems. Right? But it can still be used for communication signals though. However, the more widely used is the pulse amplitude modulation scheme. So we won't dive into more detail in this in these pulse modulation schemes. Okay. So now let's look at multiplexing systems. A multiplexing system is a way of sending multiple signals over the same channels without interfering with one another. So there are different types of multiplexing. There are four of them actually: frequency, time, code, and space. So we'll only discuss these two, and these two are outside the scope of your basic fundamentals of communication theory or the introduction to communication systems. Okay. Your FDM is typically used in CW modulation schemes, while the other one, TDM, is typically used in pulse modulation schemes. So why is that? Your CW modulation schemes are inherently have a small bandwidth. So we can fit them over very close to each other but not overlapping. So that's what's happening here. User 1 and user 2 can communicate independently of each other, okay, by using a frequency division multiplexed system. So your users can transmit at the same time, but they transmit at different frequencies. And in effect, you can actually listen to both frequencies if you tune to the right frequency. Right? And because of this, this was the earliest multiplexing scheme that was developed. Right? Because analog systems were the first ones to be introduced. And this paved the way for the idea of fixed channel assignments in frequency spectrum. Okay? And that's why we have frequency assignments for radio, we have frequency assignments for TV signals, frequency assignments for Wi-Fi, and so on and so forth. Right? So it's usually employed by CW modulation because pulse modulation, well, occupies a large bandwidth. Time division multiplexing uses the spaces in time. You fit a lot of pulses over a period in time such that your first user will not interfere with the second user. So this is typically used in pulse amplitude modulation. As you can see, we can fit pulses as long as there are spaces in the uh, as long as there are spaces in our timing, in our time domain, basically. So it involves scheduling your transmission, right, and synchronizing between other users. So you transmit whether your pulse modulated signals of the other users are turned off. And this is typically used with PAM and PCM. Right. A demonstration will be provided when we talk about when we meet again in the lecture. Okay? And that is the end of this lecture. If you have any questions or you need any clarifications, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.